All right, morning everyone. Hopefully everyone enjoyed the nice weather this weekend. This is the time of the year finally. We get to almost June that, the weather's going to become an issue with you wanting to do work. I went through all the ed puzzles. Thank you for the responses on, what's working, what's not working. It's interesting that, some people love certain things, other people hate that same thing. If you like crash courses, they literally have pretty much a video for every topic. I do know they go fast. There's sometimes a couple of them that I think work well for what we're doing. So we only really have one unit left, so we don't have much left. So maybe you have one, if that. I am seeing copying of ed puzzles. I don't know if someone's just giving answers out or whatever. It doesn't really matter to me. But they're giving completely wrong answers, and then it rolls through that whole class. Specifically, Block 4, seeing lots of it with you guys. All right, so just, remember, your work is your work. Make sure it's authentic. It only helps you if you actually do it. I'm starting to see people, what I believe are doing is not watching the video and just typing in an answer on the ed puzzles. That's a strategy, but it's not working out well for you. Tomorrow, I'll have a Zoom session, like 10 to 11 probably, if you have questions for the test that's on Thursday. All right, but basically bring questions. There's really nothing, it's hard to, choreograph, a Zoom lesson any other way. So if you have questions about certain things, and don't say, I don't understand anything. Come in with specific questions for it. All right. Thursday, 9:30 to 11 is going to be your test. Basically, we're having issues of people missing their alarm and this and that and every excuse under the sun. So if you miss it from 9:30 to 11, you have a 6-page paper as your alternate assignment. I will give you a topic to write on that's appropriate for this unit. So if you like writing, then that's good. And it's going to be notated, not just what you think. So that's your choice on that. Okay. Only official homework tonight is ed puzzle notes. Going through, we have, I think there's one organic reaction, esterification, which is making esters, and then a couple loose ends to tie up. And we are essentially done with organic. This has been interesting. Organic is one of those units that normally we need lots of feedback from you to ask questions. But you have to do the work and you have to check the work yourselves. Is kind of how this remote thing's working right now. So, all right. So just a reminder, tomorrow at 10 a.m. It's really, I want to say like an office hour type thing. You come in, you have a question, you can stay, you can leave. It's up to you. You want to hear other people's questions, completely up to you. But it's not really something that's guided and instructed by me. So just so you know for that. Okay, here we go. Here's the bell ringer. Okay, name of this bell ringer. So first thing you want to do is count up the carbons. 1, 2, 3, 4, 5, 6. Prefix for 6 is hex. All right, is it ane, ene, or ein? And this is important. Typos. I don't know if it's typos, misspells, or you're thinking the other thing. Changing it from an ane, ae, or y completely changes the molecule. Or changing it from an ol to an end in an al completely changes the molecule. So you got to have that attention to detail. It's going to make the molecule wrong. So this one has 6, so prefix is hex. Is there any double or triple bonds between the carbon atoms? Nope, so it's hexane. So that's our base, is hexane. Now, we have this functional group right here, which is a carbonyl group, which is on the 3rd carbon. All right, remember, if it's just a carbonyl or a double bonded O and a middle carbon, then that's a ketone. Remember, ketones change the ending to end in -one. So it's hexane, -one. So you drop the E and add ONE. And then the only other thing you have to do, because there's multiple places where this double bonded O could go in the middle, you have to count what number it is. So from the left side, we count 1, 2, 3, 4. We call it 4-hexanone. If we count from the right side, it's 1, 2, 3-hexanone. We have to count from the side that makes the shortest number possible. So this molecule is 3-hexanone. Okay? All right. Here we go. Types of reactions. Esterification is making esters. Remember, esters end in that it's a branch. So it's like methyl, ethyl, propyl, butyl, and they end in OATE. All right, that the other side of the molecule, you have the C double bonded O next to an O. All right, so it's making one of those. So what do you need to make an ester? You need an organic acid, which has got that C double bonded OOH, and you need an alcohol. All right, and what it actually produces is it's going to produce an ester and water. People who took living environment, you've heard of something called dehydration synthesis. All right, that's the process of joining two molecules by removing a water, and then a different bond is created and it joins them together. Okay, so I really think the hardest part of this whole process is naming the ester, and I said that when we went over esters, and you really want to, use your review book. You can use your papers that you have. All right, you can go online and look at those. All right, but here is a reactant. So we have an organic acid and an alcohol. All right. What I'm going to do on the video is I'm going to pause this and ask you for the names of these because it's a good review for you. Now notice I color-coded it. So this is where, and it doesn't matter. You can get the OH from here and the H from there. We're not going to get into splitting hairs here with you guys with this. But basically, you got an OH and an OH. From that OH and OH, you're going to pull out a water. So you're going to pull out two H's and an O. And then what happens is these orange are lopped off, and that's where you get the water from. And then this carbon right here is then going to bond to this O right there. So you end up with this. So you end up with this molecule basically joined together. You join the two molecules together, and then you have water as another product. All right, now naming. Once again, naming. I'm going to give you a hint, and then I'm going to ask you to name it. All right, so you know it's an ester, so you know that it's got to end in OATE. All right, so you got the branch side and the base side. All right, so you got the base side here with the O's. So all the O's go to the base side, and then the branch side gets named separately. All right, so stop, name. All right, now here, the branch here is a one-carbon branch, so one carbon branch is called methyl, and then a two-carbon ester is called ethanoate, so this is actually methyl ethanoate. All right, okay. Polymerization. So this is one of the things I wanted you to watch the crash course for, because they have the video ability to go into a couple different things and I can't. But basically all polymer is the same unit repeated over and over and over again. A 1-unit polymer is called a monomer. A 2-unit polymer is called a dimer, and then 3 or more is polymer. And you can get these things up to thousands and 10,000s of the same unit repeated again and again and again. All right, so a polymer is a very long chain molecule made up of these monomers that are joined together. All right, we're not going to go into naming all these things. Plastics, there's lots of natural polymers, but you've heard of polystyrene. All right, that's many styrene molecules. All right, polybutadiene is many butadiene monomers and such. Okay, so there's 2 ways to join these things. And I'm just going to show you the names at the top. There's addition polymerization, or adding polymers together. And then there's condensation polymerization, which is condensing it together, which is basically dehydration synthesis. All right, just you don't have to know the specifics of these things, just showing you that basically when you have an addition polymerization, you're going to get the same unit. So N just means some number. It can be 2, it can be 257. It can be 5,226. It doesn't matter. All right, and you have this molecule right here. So this is a vinyl chloride right here. All right, when you join many of them together, you get polyvinyl chloride, which is PVC. All right, and then the N, instead of being a coefficient in the front, becomes a subscript at the end. It's just that unit repeated over and 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 over again. All right, and then another way to do it, you got the TFE, tetrafluoroethane. You got some number of them. I think in actual Teflon, this number is 500, I believe. Might be 1,000. I don't know. I don't remember. So it would be 500 of these units, and then they're joined together, 500 of the units together as one. All right. So that's the poly. You don't have to know the name of it. Polytetrafluoroethane. All right. It's the scientific name for Teflon. But all you have to know is that addition polymerization is just you're adding the same unit together again and again and again. So if you see something in parentheses with some number next to it, usually a large number, you know it's a polymer. So that's it with addition polymerization. It's pretty quick, pretty simple. Condensation polymerization. So if you look here, these are all the same molecule. All right, they got the C, and I'm not going to go into naming these things. You got the organic acid on this side, you got the alcohol part on that side. We're not going to go into naming it, but you have 1, 2, 3, 4, 5 of these. All right. Now, in dehydration synthesis, just like we saw in the esterification, you're going to take an H from one of these and an OH from the other. all right? And then you end up joining it together. You're gonna do the same thing here, H and OH out, join them together. You get the H and the OH out here, you join them together. You get the H and the OH out here, join them together. All right, so now you end up with, now you're gonna have 1, 2, 3, 4 things joining together, so that's why you end up with 4 waters. And then you get 4 of the same unit repeated over and over again. All right, and you can write it like way out like this, or you can write, we're never gonna have to write it. You just have to be able to recognize it as a polymer. That's really all you're doing. So condensation and addition polymerization are very similar. They're making a big molecule. All right, these things can get really, 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 really large. All right, like the polyethylene, the high density HDPE bottle that they talked about in the crash course video. All right, the reason why HDPE and LDPE, high density and low density, is the size of this chain right here. All right, how many of the repeating units you have. All right, HDPE has many more, and LDPE has less. All right, quick review, saturated and unsaturated. We did talk about that before. Alkanes are saturated, alkenes and alkynes are unsaturated. All right, and it's always really saturated with respect to hydrogens. All right, so alkanes are the only things that are going to be saturated. All right, and you know they have single bonds between the carbon atoms. All right, which means they have as many H's as they possibly can hold here. Unsaturated is alkenes and alkynes. All right, so they're gonna have a double bond or maybe even a triple bond. I'm talking about this now because there was a big issue a few years ago with trans fats, and trans fats actually has to do with the molecular shape. Trans fats result from a process called hydrogenation, which we did talk about briefly. Basically, it's taking a molecule, an alkene or an alkyne, and adding hydrogen to it. All right, but it's partial hydrogenation. It's like if you've heard of partially hydrogenated oils, all right, they partially hydrogenate, and they're trying to get certain characteristics. Usually they're trying to turn it from a liquid to a solid. They don't want it to be a liquid. They don't want it to be like an oil. They want it to be like a solid fat type thing for whatever reason. All right, so a cis fat or a cis molecule, any cis molecule in chemistry, ends up with a double bond. We'll use it as a double bond between the carbon atoms, and both the hydrogens are on the same side. So the top side or the bottom side, it doesn't matter. And what that does to the actual molecule is it puts a bend in it. All right, it puts a bend in it, which means it's going to take up more space. Its volume is going to be a little bit bigger. So that's what a cis fat is, where the hydrogens are on the same side of the double bond. Or it could be something else. We're just talking about it in terms of fats. All right, where a trans fat, you notice you got the double bond here. Here you got a double bond as well. And in the trans fat or the trans molecule, the attachments are on opposite sides. So what that does is it makes the molecule take on a straight shape. All right, which means you can pack more into a smaller space. All right, for our application, this would be like an oil or a liquid at room temperature. This would be like a solid at room temperature. All right, if you're eating chips, you don't want a liquid fat rolling off the chips and make it soggy and wet and things like that. So they partially hydrogenate it. Okay, so that's where that trans fats or trans fatty acids, some people might know about, people that are into, you know, eating certain things or whatever. All right, partial hydrogenation is usually not a good thing. Partially hydrogenated things are like margarines. All right, margarine is taking, all margarine is, you know, I've heard people say it's plastic butter. All right, and we can go into all kinds of issues of which one's better for your body or whatever, and I don't know if there's really a winner, so to speak, between margarine and butter. All right, but margarine can either be partially hydrogenated or it can be completely hydrogenated, where if it's completely hydrogenated, you take this double bond, you add a hydrogen here and a hydrogen there. All right, what it does is it takes it, because of this molecule being flatter and being able to squish in better. All right, it takes a liquid fat, such as, let's say, peanut oil, and now it turns it, because it can be packed tightly together, it turns into a solid fat at room temperature. All right, instead of being a liquid that you would pour on your toast, it's now a solid that you can spread on your toast. It is really what it is. That's what margarine is compared to butter. All right. Solubility, remember, like dissolves like. Generally speaking, hydrocarbons are nonpolar. So remember, hydrocarbons are compounds with just carbon and hydrogen. So like your alkanes, alkenes, and alkynes. Those things are generally nonpolar. All right. Here's an oil spill or a gasoline spill. You can see the oil slick on top of the water. All right, you guys have seen this small scale, maybe in a lake or a pond, or maybe even just in a puddle. All right, if you drop a little bit of gasoline or a little bit of oil, it'll make that sheen on it. And it's really hard to get those to, to clean up, so to speak. There are compounds in this unit that are soluble in water. Alcohols are soluble in water, and then things called organic acid. Alcohols, I always refer to things that people drink. They will definitely mix with water. Organic acids, the simplest one is acetic acid, which is vinegar. Those are soluble in water because they are polar. These things are polar, where these ones are non-polar. Okay? And then basically, melting points and boiling points, the larger the molecule, the higher the melting point, boiling point. All right? Alcohols and organic bonds, because they are polar, have stronger hydrogen bonds. All right? Amines have weak hydrogen bonds. I'm not going to really worry about the amines. All right? So the presence of hydrogen bonds increases the strength of IMS. All right, so alcohols and organic acids, because they are polar, are going to have higher melting points and boiling points. Okay, that wraps up our organic unit. All right, your organic unit. One last thing I want to talk about the organic unit is your reference tables. I have not referred to this yet for many reasons. All right, but on your reference tables, I didn't put it on the slideshow, sorry. On page 7, all right, this is for the Regents kids. Honors kids, you can look it up. It doesn't really matter. They give you the prefixes for the organics, all right, on table P. And then on table Q, they give you the general formula for the alkanes, which, I don't know. I'm not sure it really helps if you don't understand it. That's why I really don't teach it with that. And then if you look at the next page, all right, they kind of give you functional groups here. All right, they kind of give you functional groups here with their general formula and a sample molecule. But if you don't know what you're talking about or what you're looking at, this really doesn't help you out. This is more of a good reference tool versus a teaching tool. All right, so when you're taking your test on Thursday, you might want to have your reference table out and available to help you out. But R's, one thing I want to talk about is these R's. All right, R's don't mean anything. That just means a chain. If you look down here, it says a bonded atom or a group of atoms. Usually it's carbons with hydrogens on them, right? But it can be other things and more complicated molecules. We don't deal with those complicated molecules at our level. All right, but like here in an ether, you got R and R prime. They don't have to be the same molecule on either side or the same number of carbons on either side, but they're just something that's there. Okay? All right, so that's it for that. Remember, tomorrow, if you want, kind of quote-unquote office hours from 10 to 11. If you have questions, and then we should be good to go. All righty, have a good day. Stay cool.